The question that I have is, could you talk about two force members and springs and rigid body static problems? Let's talk about the special structural elements. I want to talk about two of them here. The first one is called the two-force member. So here are three examples of two-force members, and we already talked about some of them. In the first example here, we have a rigid curved member that is supporting this structural element through pins at point A and B. So this special element is like the 2x4 but is curved. And the last one, we have a similar arrangement. This is exactly like a 2x4. So basically a straight rigid member supporting the structural element through pins at the ends. And in the middle picture, we have a structural element which is being held by a cable at the end. These are all examples of two-force members. Why? So let me take the first one here and explain why we call this a two-force member. If I were to take this rigid member out of the pins and draw the free body diagram for it, these are the forces acting at the ends of that member. So this is the pin at A, right? Therefore, there will be two components of the forces, AX and AY. And similarly, this is a pin, and there will be two components of the forces, BX and BY. Remember, another way of representing the forces on a pin is to represent them in terms of a single force with a magnitude FA and a direction theta, right? So that's what I have done here, both at pin A and pin B. Since we have not done much with the equilibrium equations for these members yet, you may not understand this completely at this point, so just bear with me. We will in a little bit. But basically, if you have a member like this, which are subjected to two forces like this, FA and FB, right? And it can be shown using the force equilibrium equations that FA and FB must be equal to each other. That means its direction must be equal to each other, and of course equal and opposite, and the magnitude must be equal to each other. All right, so the first thing you can show using the force equilibrium equation. And the second, using the moment equilibrium equation, you can show that FA and FB must have the same line of action. In other words, they should line up. Same fundamentals apply to the cables and the 2x4s which are straight. Basically, these members are subjected to two forces, one at A and one at B, but they are equal to each other and they line up. When you have rigid members like this, one caveat is that these connections must be pins, not fixed. So how does this help us in developing the free body diagram for the structural element like this? Remember, in developing a free body diagram, we need to take this out of the supports and mark the forces acting on the supports, right? So if you have a two-force member supporting the beam, then the force acting at that point, at the support point, is simply a single force like this, and the direction of the force is dictated by the direction of this member. So coming back to this diagram, the direction of the force at point A in this first example is going to be along the line connecting point A to point B, in other words, this line right there. And the direction of the force in the cable is in the direction of the cable, and the direction of the force in the third example, where you have a 2x4, straight 2x4, is in that direction, in the direction of the 2x4. So this allows us to represent the force at the support in terms of just one unknown. The second special element that I want to talk about is a spring, specifically an elastic spring like shown over here. So here we have a structural element that is supported by a spring. The spring connects to the structural element at point A. So when I want to develop a free body diagram for the beam, I would take the spring off the beam, the structural element, and represent the internal force by something like this. So the nature of the force here is very similar to what we had in the cable system. So there's going to be just one force, FA, and that FA is going to be acting along the direction of the spring. From your physics class, you might recall that FA, the force on the spring, can be related to the spring constant and the deflection on that spring. For an elastic spring, the force displacement relationship is linear, right? and the slope of that linear line that passes through 0 is what we call the spring constant K. So in an arrangement like this, the spring is likely to experience an extension, delta A. So the force on the spring then is given by K multiplied by delta A. This linear relation, of course, is true only for linear elastic springs. There are nonlinear elastic springs, which is beyond the scope of this course.